All right. So today we're going to talk a little bit about the secant function. So the secant function, we can think of it in a variety of ways. The three main ways that we've thought of it so far is using kind of our right triangle trig definition, where we thought of it as the hypotenuse over one of the sides, the adjacent side, or r over x. Our unit circle definition, so in that case, remember our r is 1, so then secant becomes 1 over x. And last is our reciprocal definition. So we know that cosine is x over r. Reciprocating that means switching numerator and denominator, and that would give us r over x, which is exactly our secant function. Okay, so these are kind of the three main ways that we think of the secant function. And now let's go ahead and use our good old unit circle here to see if we can't start getting an idea for what the secant function looks like on a graph. All right, so again, we're going to be plotting points that are of the form theta, secant of theta. So to start out with, when theta is 0, so when we're sitting over here at 0, our x is 1, 1 over 1, reciprocating that, gives us 1. So the first point we have on there is 0, 1. Next, let's look at pi over 6. At pi over 6, our x value is negative, our x value is square root of 3 over 2. Reciprocating that is 1 over the square root of 3 over 2, or that just means flipping our numerator and denominator. So we get 2 over the square root of 3. When we rationalize that, that gives us 2 square root of 3 over 3. For pi over 4, our x value is square root of 2 over 2. Reciprocating that gives us 2 over the square root of 2. And rationalizing that gives us 2 square root of 2 over 2. So there's our next point. And at pi over 3, we've got 1/2. Reciprocating that would be 2 over 1, or just 2. So there's our next point. Now let's think about what happens at pi over 2. Well, at pi over 2, our x-coordinate is 0. Reciprocating that would be 1 over 0. Division by 0, that's not good, which means our secant function is undefined at pi over 2. All right, so here's our points in the first quadrant. Just for fun, let's keep going and look at what's going on in the next quadrant. So our next angle there is 2 pi over 3. Now remember, we're looking at our x values. Our x value is negative 1 over 2, and we're going to reciprocate that. That's going to give us negative 2. Ooh, not 3, negative 2. All right. So next, we have 3 pi over 4. And if we're looking again at our x value is negative square root of 2 over 2. Reciprocating that gives us 2 over negative square root of 2. And when we rationalize that, we get negative 2 square root of 2 over 2. So there's our next point there. All right, let's just do a couple more. When we are at 5 pi over 6, then our x value is negative square root of 3 over 2. That's going to be 2 over negative square root of 3. Reciprocating that, I'm going to get lazy and do some copying, is going to give us negative 2 square root of 3 over 3. All right, and then let's see what happens at pi. So at pi, our x-coordinate is negative 1. When we reciprocate that, we'll have 1 over negative 1, which is negative 1. So these, let's make them all blue, are going to represent our points in the second quadrant. All right, now we could keep going, but again, we have this great program that'll go ahead and sketch our graphs in for us. So let's go ahead and do that and see what the secant function looks like. We'll look at that. So here's our first quadrant. Here's our second quadrant. This would be our third quadrant, and then our fourth quadrant. So if we're thinking about it from quadrants, first quadrant, second quadrant, third quadrant, fourth quadrant, it's pretty straightforward, I hope, to see that this has a period from 0 to 2 pi. In other words, the period length is 2 pi. This is going to repeat every 2 pi. Now, sometimes it's easier to see that by looking at kind of one upward little U-curve and one downward little U-curve. So when we do that, we can look at x equals negative pi over 2 to x equals pi over 2. Oops. 3 pi over 2, excuse me. Sorry. 3 pi over 2. Okay. And notice that between these two bars, we've got one upward and one downward. So that again is a full period. So that full period is going from negative pi over 2 to 3 pi over 2. Adding those together gives us 4 pi over 2 or 2 pi. So either way we look at it, our period is 2 pi, okay? Now again, like our tangent and cotangent function, we're not gonna worry about amplitude with these. We are gonna worry about period. The other kind of cool thing to look at, I'm gonna turn off some of our points here and just keep the secant function. Okay, remember that we said that secant is the same thing as 1 over cosine. This is just a nice representation of that. Notice that those two graphs show the exact same thing. Okay. The other thing that's kind of interesting to look at when we're looking at secant is actually to compare it to the graph of cosine. Okay. All right, so first of all, that's just lovely right there. But a couple of things to notice about cosine. Every time that cosine is 0, so for example, cosine is 0 at pi over 2, that's where we get a vertical asymptote, meaning secant is undefined. And that makes sense because remember, over here, when cosine was 0, such as at pi over 2, the reciprocal of that, 1 over 0, is undefined. All right, so this is our lovely secant graph. Okay, looks like these fun little shapes. Has period of 2 pi in length. It's the reciprocal of the cosine graph. Everything else about it, we can think about graphing using transformations, just like we've done with sine, cosine, tangent, and cotangent. Okay, we can reflect secant. If I put a negative out in front, that's going to reflect across the x-axis. Let's see what that does. Woohoo! Okay, so it looks like they're moving left and right in my kind of brain, but really what's happening is those tops are flipping to the bottom and the bottoms are flipping to the top. Okay, if we put a negative in front of the x inside the argument of our secant function, that's going to represent a y-axis reflection. Now take a look at this. Is a y-axis reflection going to do anything? It does nothing. Why is that? Well, because this function is symmetrical about the y-axis, meaning if I fold it in half along the y-axis, those two halves are going to match up. Okay, what else can we do with this function? Well, we can move it up and down. Okay, so if I want to move it up 2, I'm going to do 2 plus. Notice that that moved my function 2 units up. If I want to go down 3, I'm going to add negative 3. Again, notice that that moves my function down 3 units. Okay. Now, vertical stretching and shrinking, we can do that. Oh, look, that makes it kind of taller and skinnier. Moves it a little bit. So that's vertical stretch of 2. A compression of 1/2 compresses everything down, makes them closer together. It's easiest to see that if you look at kind of the distance between the top U's and the bottom U's. Notice that when I put in 1/2, that distance gets smaller, so we're squishing everything together. Okay. All right, if I want to move this left and right, I'm going to do something inside with the x. So for example, if I want to move it to the left pi, if I want to move it to the right pi over 4, I'm going to do that. So that moves our function to the right by pi over 4 units. Okay. If I want to move our function to the left, pi over 2 units, I'm going to add pi over 2. So again, notice that's moving our function pi over 2 units to the left. Okay, the last thing we can do is mess around with our period. So one way to think about our original period is it goes between x equals pi over 2 and x equals 3 pi over 2. Okay, so there's our original period. Okay, now inside there's kind of one set of the up U curve and the down U curve. Let's look at what happens when we do some horizontal stretching and compressing. So instead of secant of x, let's do secant of 1/2 x. Oh man, okay. What happens there? Notice that we've made this wider. or we have done what to our period? We've increased our period or made our period wider as well. Okay, now our period, if we look at kind of this up curve and this up curve, now our period's going from negative pi to 3 pi. There's our period now, meaning it's 1, 2, 3, 4 pi units long. So we're going to do our period the exact same way that we did before. We're going to take our original period, 2 pi. Then we're going to divide by the horizontal multiplier. 2 pi divided by half is 2 pi times 2, or 4 pi. All right, what's going to happen when instead of 1/2 pi, I do, or sorry, when instead of secant of 1/2 x, I do secant of 2x. Let's take a look. Oh man, so there's our original, there's our new one. Notice that our new graph, we horizontally squished it down together. So our original period was negative pi over 2 to 3 pi over 2. One way to think about this is look at how many little wave functions are in there. These aren't wave functions. How many of our little U curves are in there? I've got 1, 2, 1, 2, even though half is here and half is there, it's still 2 of those down U curves. So 2, where this 2 comes from, 2 of our complete functions now fit inside our original period. Okay. The other way to think about that is, what is our period now? Well, our period has been cut in half. Okay. So our period is going to be 2 pi divided by 2, which is just pi. So our period should go from 0 to pi. That should be one way to look at our period. And if we look at this, we do have one complete down and one complete up. It's just split in half. We've got the right half here and the left half here. So just like all the other things we've done, to find the period of secant, we're going to take the original period, 2 pi, and divide it by our horizontal multiplier, in this case 2. All right, that's secant. We're going to look at cosecant, and then we're going to do some examples of graphing these using transformations.